Welcome to Your Space Journey, where we venture into the future of space exploration and the incredible leaders who are taking us there. Here's your host, Chuck Fields.
Hello, thanks for joining me today for Your Space Journey. Last month, on October 20th, 2020, NASA's OSIRIS-REx spacecraft made history as it briefly landed on the surface of Asteroid Bennu to collect samples for return to the Earth. Now, it's not easy to travel over 200 million miles to land on the surface of an asteroid that takes light over 18 minutes just to reach from the Earth. But NASA did it. Now, years in the making, this mission had to overcome several challenges, but more are yet to come as the samples are returned to Earth. They're actually scheduled to head back in March of 2021 for a 2-year journey, arriving at the Earth in 2023. Now, today I'm pleased to introduce Dr. Jason Dworkin, the project scientist for OSIRIS-REx and NASA's senior scientist for astrobiology, as he describes this incredible mission in more detail.
Your Space Journey.
Jason, thank you so much for joining me today.
Thanks for having me.
My pleasure. First, I have to say congratulations to you and your team for your incredible success so far for OSIRIS-REx.
Oh, it's been beyond our expectations. It's really phenomenal.
Wow, I can't imagine. Now, I understand as of right now, the samples from Asteroid Bennu are safely stowed in the spacecraft sample return capsule. Now, it's been, obviously the last few weeks have been busier than anything. How are you and the team feeling right now?
Elated. The sample acquisition, the act of tagging the asteroid, the touch and go maneuver, was as good or better than our best case simulations. Rehearsals went phenomenally well. Collection was remarkable. The spacecraft touched the asteroid on schedule in a very safe spot. The spacecraft had extended a 3-meter, about 10-foot long pogo stick, the TAGSEM arm that has like an air filter on the end of it called TAGSEM, the touch and go sample acquisition mechanism, and in fact penetrated the surface by perhaps up to half a meter.
Wow.
Deployed a jet of nitrogen gas to fluidize the regolith and get it trapped inside of the sample container. There was I usually describe it as a 10-foot long pogo stick, but in fact the surface of Bennu was so soft the pogo spring didn't even compress at all.
Wow.
It just kept ascending into the surface until the backaway thrusters activated and the spacecraft left the surface of Bennu with a sample container literally overflowing with material. So much so that we had to skip the mass measurement maneuver, which requires spinning the spacecraft up, because that would have flung out sample. And having sample is better than knowing how much you have sample. But by all the looks of it, we have well above our 60-gram requirements, probably hundreds, if not thousands of grams. We'll know for sure when it comes back to Earth. It's just phenomenal. So the sample is tucked away safely in the sample return canister. Mm-hmm. The spacecraft is drifting away from Bennu, and then will depart this spring for Earth.
Well, we cannot wait. I know it's going to be a long journey. Now, before we talk about that mission, though, I want to go back and just talk a little bit more about you, because you've had an amazing journey since your days as a third grader, fascinated by dinosaurs.
Oh,
Can you tell us more about how you first became interested in space and astrobiology?
Well, let's see. So space, that came about, I'm a child of the Apollo era. And so I remember Apollo launches very dimly. And certainly I remember some of the moon landings, perhaps, and Apollo-Soyuz and Skylab. Mm-hmm. And so I was always very excited about space. And there's a story, I don't remember it, but my mother tells me. She asked me if I wanted to go into space, and I said, no, it would be too loud. But I would like to look at the samples they'd bring back.
Nice.
I have no recollection of that, but based on my personality type, I like knowing when things start and how they start. Mm-hmm. And so, you mentioned the dinosaurs. And so I was, as most children are interested in dinosaurs, right, because they're inherently interesting. I thought, well, let's see, what's the first dinosaur? Okay, what came before the first dinosaur? Well, what came before the first life? How did that get going? And so just trying to understand beginnings is what brought me to the origin of life. The origin of the universe is also interesting, but that requires more math than than is in my skill set. But also, I really like being able to see and touch something. So I find looking at samples, things that come from other worlds in the laboratory, immensely satisfying, more so than looking at photons. Because, again, the way my brain works, I find being able to witness something that you can visually see thrilling. And so studying samples that are literally older than the Earth, literally older than dirt, is just exhilarating. And being able to look at samples in new ways and answer questions that were unanswerable years ago is what my career is about.
Oh, I think that's incredible. And what a great fit for OSIRIS-REx. Now, this mission itself, you've been involved for more than a decade. Can you just tell us more about how this mission itself came about?
Well, the mission has a long history of several iterations. Some of the concepts dated back to the 1980s with had a sample from the surface of a comet. It then evolved into a mission concept called OSIRIS, which was a partnership between Lockheed Martin and the University of Arizona. And that's when I got involved in 2004. That mission was in many ways naive and overly ambitious and was, for good reason, not selected by the agency. We then reproposed and brought Goddard in to manage the mission, but we're still not selected because we demonstrated that we couldn't fit in the cost box under the Discovery cap, which is a mission classification in NASA Planetary. Mm-hmm. Instead of the mission OSIRIS, the mission Grail was selected, which was a fantastic lunar exploration mission.
Right.
So we demonstrated that in a proposal that we couldn't do it, and in fact, now that we've been to Bennu, we realized that had we been selected under this call with the spacecraft that we would have been able to build under that Discovery cap, the mission would have been incredibly difficult. We would have still gone to Bennu, but not had such a capable spacecraft. We would not have had the camera system, the LiDAR system, the navigation system that was required because Bennu was such a challenging object, it turned out. So we wrote a new proposal that was selected by the agency in 2011 and spent many years developing the concept, reducing risks, and then finally building the spacecraft, launching it in 2016, arriving at Bennu in 2018, and then sampling this year.
See, I think that's incredible. Now, the Asteroid Bennu itself, is what I understand, it's about the size of the Empire State Building, about 1,600 feet in diameter. Can you tell us more about Bennu and why it was chosen for this mission?
So when we were developing the mission concept, we had to do this many years in advance. Mm-hmm. The goal was to get a sample of the early solar system, uncontaminated by landing on the Earth, something pristine. So the choice is to go to an asteroid. At the time, there were 500,000 asteroids. Now there are more than almost 1 million that have been discovered. Mm-hmm. So we needed an asteroid that we could get the spacecraft to and back on a launch vehicle that exists in a time span that was reasonable. Right. So that makes us have to go to a near-Earth asteroid with good orbital parameters so that you can get there and back. Mm-hmm. And that brings it down from 500,000 to 190 different asteroids that are worth consideration. Mm-hmm. Of those, we needed one that was large enough that it had there's a relationship between the asteroid size and the asteroid rotation rate. So asteroids that are smaller than 200 meters tend to spin very, very fast, as much as 1 revolution per minute, wow, which makes navigation very, very difficult. And since our goal was to sample regolith, the gravel and dust from the surface of the asteroid, fast rotators wouldn't have those. So then that left us with 26 asteroids. We wanted one that was definitely primitive and from the early solar system. Of those, we had spectra from ground-based and space-based observatories that give 5. Of those 5, Bennu was the best characterized, had the lowest inclination, so the lowest delta V, the easiest to get to, the least energy, and was the best choice. Interestingly, our backup choice was the asteroid Ryugu, which is where the JAXA Hayabusa 2 mission went to. So it'll be really fascinating to compare those two samples when they come back.
Yeah, Jason, I understand you actually are involved with the Hayabusa 2 mission as well. Can you tell us, how are you involved in that?
So I am deputy on a sub-team. So this is a sample analysis soluble organic material sub-team. It's part of the mission, but only sort of.
Okay.
So Professor Naroka from Kyushu University, he is head of the soluble organics team. I'm his international deputy. So I'll be helping analyze some of those samples when they come back.
And that's incredible. And I understand those are actually coming back next month. So December, we're going to get our first samples back. Oh,
very, very exciting.
That's going to be so exciting. And going back to Bennu itself, you mentioned launch 2016, started orbiting in 2018, December. Now, obviously, when it started orbiting, it was able to map down, I understand, to about 2 centimeters resolution, which is incredible.
A little better than that, but yes.
Really better than that. Wow. And you got some surprises because you were looking for, landing sites, and you were surprised by the rocky surface. What was that like? I mean, obviously the research was great. You got there and the regolith was perfect. But when your team found out, oh my gosh, where we're going to land, how did that affect, I guess, the overall mission and the planning and the timeline?
That was a gut punch. We had done so well on predicting the shape of Bennu and the rotation orbital parameters, but we were so very wrong on how smooth an object we thought it was. We measured something called the thermal inertia, which is basically how fast or how slow the surface heats up and cools down going from day to night and night to day. You can use that to measure and predict the grain size. And we predicted a few centimeter average grain size, which is perfect for our sampling device. And we were nervous about not having any features to navigate around when that it might be too smooth an object to actually do navigation. And so we had all these backup plans in case it was too smooth. Well, it's quite the opposite. Yeah. So our thermal inertia measurements were accurate. Our interpretation was wrong. And that's related to how friable, how fragile, how loosely bound together this asteroid is. It is a rubble pile, but more so than we had pictured. And you have proof of that by how the spacecraft spring didn't even compress, that it just sank into the top half meter of a surface or so. And so, Bennu was full of surprises. We had that. We had particles being ejected from the surface, which had never been seen before on an asteroid.
Right.
We had expected to possibly see dust plumes. We had a dust survey, see if there's cometary-like activity. We didn't see any dust. We did eventually see rocks, which was another surprise and a moment of terror. But it turned out to actually be not hazardous for the spacecraft, but a real bounty for the science. Or you can use those, one, understanding what the rocks, why they're coming off, and that there may, in fact, be a Bennu meteor shower on the southern hemisphere of the Earth every September.
Wow. A
very small one. People are still looking to see if they can figure it out. Very small, though.
That's incredible.
But also, we were able to get detailed orbital parameters or gravitational parameters from the orbit of these rocks to understand the internal structure of Bennu much better. So it's been a scientific boom.
Oh, Jason, well, you mentioned again, I can't wait till these samples get back. I understand that's going to start the journey back in March of 2021. It's going to take, till 2023 till they land, hopefully, in Utah. And I understand these will be stored, the samples, at NASA's Johnson Space Center in Houston. And I understand you actually have a role for how to store it and the distribution of the sample. Can you tell us a little bit more about that?
Right. So I'm actually a sample scientist. So my scientific role on the mission actually begins when the sample comes back. I'm a cheerleader for the science now. I don't actually do much of the observation of the analysis of the in situ measurements. Mm-hmm. We're conducting a trace study to see exactly when we leave. We had baselines in March. However, we've discovered a lower energy trajectory that would get us back around the same time. That leaves a little bit later. So we're conducting that trade now, but it'll still be around September 2023, and definitely at the Utah Test and Training Range outside Salt Lake City, Utah. The sample comes back via parachute, landing in the Utah desert. The spacecraft diverts away from Earth and orbits the sun, and that would be an asset that NASA can use if it chooses to. The sample is then recovered and, as you said, brought to NASA Johnson Space Center in Houston. I've been helping the curation group come up with requirements and plans on how to archive the sample. Of that sample, 25% goes to the science team to answer our 50-some hypotheses on Bennu and early solar system and what it can tell us. But the remaining 75% is archived and available for the international community, so that perhaps your listeners or their children or grandchildren can make life choices to analyze the samples.
I think that is incredible because I've heard that 75% sample. Yeah, because people who haven't even been born yet may be the scientists that discover something about the sample collected just last month. That is incredible.
This is the benefit of sample return missions. For example, my laboratory at Goddard analyzed some samples from the Stardust mission, and we discovered glycine from the simplest amino acid from Comet Bill 2. That was never a mission design, never a mission goal to look for these specific organic compounds. And so that's something you can do as technology improves when the sample comes back. An even better example are the Apollo samples. And so samples are being opened now that were archived for 50 years.
Wow.
The principal investigator of that in my research group, Jamie Elsula, she wasn't yet born when the samples were collected. And so she will be using these samples collected before she was born, analyzing them with techniques that were not invented until decades after they were collected, to answer questions that were unanswerable in the 1970s when samples were collected. So it's really remarkable. And my absolute favorite thing about OSIRIS-REx, we'll answer a lot of good questions about planetary science and astrobiology, but we will give the future generations the ability to ask questions we can't even imagine.
Oh, I love that. Jason, if I could ask you one last question, do you have any advice that you would offer for, say there's kids out there or younger adults that are interested in pursuing a career in astrobiology or other science? What advice would you offer?
I get this question a fair amount from students who write me. And absolutely, pursuing a career in astrobiology or planetary science has many different paths to get to it. Study one of the subfields, chemistry, biology, geology, astronomy, whatever that is, and know that really, really well. Learn to write and communicate. Become a better public speaker than I am. That's really important. Become a really good writer, critical thinker. Learn a bit about budgets and spreadsheets and Excel. But most of all, capture a passion for your studies and do whatever you can to further those goals. So I was interested in the origin of life. I got myself a student internship. I studied biochemistry as a way to get access to origin of life questions and found my way in to use every advantage I could come up with to enter this field. I've been extremely fortunate to have had those advantages and be able to capitalize on them. So I encourage your listeners to use the resources, ask for help, call up old scientists like myself and ask politely because we're not used to internet speak with a nice email and explain what you want and what you're looking for, and we can usually try to help you.
Oh, well, Jason, you're a living example. You and your team are just great examples of people who have pursued their passion for science and have accomplished just some amazing feats for this. So we're just, again, congratulations for the success of OSIRIS-REx. We can't wait till the samples get back. We'll wait patiently. But again, Jason, I just want to thank you for taking time today to join me. Thank you so much.
Thank you very much. And you can follow along more and learn more at asteroidmission.org.
Your space journey.
Wow, I really enjoyed my conversation with Jason today, and we're so excited about the OSIRIS-REx mission and the return of samples from asteroid Bennu in 2023. We cannot wait. But we're also excited about the samples coming back from JAXA's Hayabusa 2 mission, scheduled to return to the Earth just next month in December 2020. Looking forward to that. Anyway, if you'd like to stay up to date on the latest for OSIRIS-REx and that mission, just go to their website at asteroidmission.org. I want to thank Jason for joining us today. I want to thank you for joining us as well. Again, we'd appreciate it if you like this episode, if you could kindly share it with a friend. We'd appreciate that. If you're watching on YouTube, if you can give us a thumbs up, we'd appreciate it. And if you're listening on whatever podcast application, if you can give us a nice rating and a comment, we'd appreciate that too. Thank you so much for joining us today. We'll see you next time. God bless.